Hi, hello, dear students. Welcome to my class on atomic structure. It's a continuation of the previous lecture. That is from our local Indian board notes I have shown you. Now this is IB textbook. In this, how atomic structure explained, we will check it off. Okay, up to the fundamental theories and all whatever I discussed in the last class. And up to that only again in this lecture also we'll see in the IB board. Okay, let us see what is atomic structure. How the introduction is given here is Australian born British physicist William Lawrence Bragg 1890 between 1890 to 1971 has shared Nobel Prize in 1915 in physics with his father. His father name is Sir William Henry Bragg. For the analysis of crystal structures using X-rays, which led to the development of X-ray crystallography. So we all know that the familiar names for the X-ray crystallography are nothing but Bragg. William Bragg is the youngest Nobel Prize laureate on record, having received the prize at the age of only 25. In a tape recorded interview in 1969, Bragg is said, see this important quotation he has given, a wrong theory is always so much better than no theory at all. This was given by William Lawrence Bragg. So, chemistry here, what we are discussing is sometimes described as the central science. Once again, I am telling chemistry is sometimes described as central science. At the center of the chemistry lies atomic theory. So, entire center of the chemistry is lying in atomic theory, and every chemical reaction can be explained in terms of atoms. So, when you are explaining any chemical reaction, somewhere you will talk about atoms. So in this topic, we shall examine the various theories and the models that have led to our current understanding of structure of atom. This is what the atomic structure introduction given in the IB board. Let us see. The nuclear atom. So in this, what we will understand. The first point we will study in this topic is atoms contain positively charged dense nucleus composed of protons and neutrons, which are called as nucleons. Negatively charged electrons occupy the space outside the nucleus. So we will get very clarity about this electrons. And the mass spectrometer is used to determine the relative atomic mass of element from its isotopic composition. So these things we will understand in this lecture. And coming to the applications and skills here is use of nuclear symbol notation ZXA to deduce the number of protons, neutrons and electrons in atoms and ions. That is one clear information about it. Our next one is calculations involving non-integer relative atomic masses and abundances of isotopes from the given data, including mass spectra. We will see that also here in this lecture. Let us move to the nature of science. Here, evidence and improvements in this instruction is alpha particles were used in development of nuclear model of an atom that were first proposed by Mr. Rutherford. That is one important nature of the science we'll study here. Of that, periodism shifts. That means subatomic particle theory of matter represents a periodism shift in science that occurred in the late 80s, that is 1800s. That is also the important point here given. Let us move on to the background to atomic theory. You know, two Greek philosophers, Lysippus and Democritus stated about around 440 BC that matter was composed of indivisible particles termed atomos. However, no concrete scientific evidence was given to support this hypothesis, and so it was not accepted to any great degree of scientific community at the time. So that is the background about the atomic theory. Coming to the next one, Dalton's atomic theory. In 1808, English school teacher, who is the whole school teacher? Dalton, John Dalton, developed atomic model of atom that was supported by experimental data. So we understand Dalton's theory from experimental data only. This Dalton model formed the origin of atomic theory that underpins much of modern science. We shall see this topic, how this model was progressively refined and replaced over time. We'll see. Now, we'll see what is Dalton's theory. Dalton called the indivisible building blocks that comprise matter is nothing but atoms. Dalton theory summarized as first postulate, we'll see, that is all the matter, that means materials, consists of very small particles called atoms. The second postulate is saying an element consists of atoms of one type only. Third postulate is saying that compounds consist of atoms of more than one element and are formed by combining atoms in whole number ratios. That is the third postulate, telling about the chemical reactions, telling about the compounds and elements. Fourth important postulate is telling about the chemical reaction of atoms are not created or destroyed. Chemical reactions of atoms are not created nor destroyed. These are four important postulates which are given by Dalton's atomic theory. So first postulate is telling about the matter consists of very small particles called atoms. The second particle is telling about the element consists of atoms of one type only. Third postulate is telling about compound consists of atoms more than one element are formed by combining the atoms in whole number ratio. And the fourth one is nothing but a chemical reaction of atoms not created nor destroyed. The simple laws of chemical combination is nothing but scientific community in 1800s. Dalton theory explains the number of these things are nothing but laws of chemical combinations. They explained in the third postulate only that was elaborated, and they succeeded in that case. So what is the law of definite proportions, combinations? This was proposed by French scientist Joseph Proust in 1799. This law states that compound always has the same proportion of elements by mass. For example, if you measure the mass of sulfur and oxygen in sulfur trioxide, it will always contain 1 part of sulfur and 3 parts of oxygen by mass. You know, sulfur trioxide is SO3. And after the law of conservation of mass also developed. That is, matter cannot be created nor destroyed. And the total mass of matter following chemical reaction is equal to the total mass of matter before the start of the reaction. For a scientific theory to be accepted, it should not only provide an explanation of known observations, but it should be able to predict correctly the outcomes of future experiments. That's what happened in Dalton's theory. That's why Dalton theory at that time accepted. Now, Dalton is said to be used his theory to deduce another law. Dalton theory is giving a lot of advantage in this one, that law of multiple proportions. So, law of chemical combinations, law of conservation of matter, law of multiple proportions. The third one is telling that if two elements X and Y combine in different ways to form more than one compound, then the masses of X that combines with the fixed mass of Y can be expressed as ratio of small whole numbers. That is another important rule. So we have discussed that one is stoichiometry chapter in the last session, also previous chapter regarding the law of multiple proportions, law of conservation of mass, law of chemical combinations. This was actually came outside when the Dalton theory supported is given the complete details about this laws. So we'll see the examples also. The law of multiple proportions. The example C. Chemists in Dalton's time did not use the mole as a measure of amount of substance. That's the main problem. As an example, law of multiple proportions considering measuring the mass of carbon and oxygen in forming the two compounds carbon monoxide and carbon dioxide. If you take carbon dioxide and carbon monoxide, two different compounds, an experiment might measure the 3 grams of carbon combines with 4 grams of oxygen to form carbon monoxide, whereas 3 grams of carbon combines with 8 grams of oxygen to form carbon dioxide. That means here 3 grams of carbon is a fixed mass of one element, and the 4 and 8 is the masses of oxygen and carbon monoxide and carbon dioxide. That means carbon and oxygen have combined in different ratios. So that is given 3:4 in carbon monoxide and 3:8 in carbon dioxide. That means the ratio of masses of oxygen here should be observed. That is 4:8. That is 1:2. That is called a simple whole number ratio, which is the illustration of law of multiple proportions from Dalton's theory. There are so many observations done here in that theory. If you see the observations here, you'll come to know that atoms of X and Y how combines to give two different compounds, and what is the ratio of Y in the two compounds, that is said to be multiple proportions. Let us see the next theory. Thomson's plum pudding model of atom. Although Dalton 1808 postulates had merit, his theory did not answer the fundamental questions. What is the atom composed of? So Dalton's theory completely confused in telling about what are the actual composition of the atom and how atom is formed. Is there any kind of subatomic particles are there? And all means the question mark arises. Why? Because Dalton told that atom is a very small one. It is indestructible, indivisible. So Dalton is not having, at that time, Dalton not having any kind of answer for this question. So it is almost under 100 years before scientists began to gather evidence to answer this question, and before that only. One of the first leaders in the field, that was English physicist J.J. Thomson, 1856-1940, between that time, he worked at the Cavendish Laboratory at the University of Cambridge, UK, and in 1906, Thomson won the Nobel Prize in Physics for the discovery of the electron. So electron discovered by J.J. Thomson. From this history is very clear that Thomson worked on cathode rays, which he suggested consists of very small negatively charged particles called electrons. So the term actually not given by J.J. Thomson, we told Stoney. That means the term electron was originally proposed by Irish scientist George Johnstone Stoney, 1891. He proposed that one. And Thomson proposed what is now termed as plum pudding model of an atom. He said that atom was similar to plum pudding. That means a dessert eaten on Christmas Day in the UK and Ireland. With that means plum pudding is with negatively charged particles like raisins embedded in a positive region, that is pudding of the atom. You can see the picture here. In this picture, you will come to know that negatively charged particles are present here. These are negatively charged particles, and the remaining pudding of the positive charge spread over the entire sphere. So positive charge which is spread. Okay. Now, if you see this figure, Thomson plum pudding model of this figure, this is an analogy. Raisins represent the negatively charged particles embedded in pudding of positive charge. Overall, there is a balance between positive and negative charges since atom is electrically neutral. So atom is electrically neutral is one of the most important point which was given in this discussion. Now, coming to the Rutherford's gold foil experiment. What Rutherford model is telling that Thomson's model raised a number of questions because matter is electrically neutral and the presence of negatively charged particles in atoms implies that they must also contain positively charged particles. That means the search for these particles and for more detailed model of the atom led New Zealand physicist Ernest Rutherford 1871 to 1937. He worked along with his co-workers to conduct the gold foil experiments in 1909 and finally is published in 1911. And this experiment tested Thomson's plum pudding model by placing thin gold metal foil in an evacuated chamber and bombarding it with alpha particles. That's what we'll see in this figure. Alpha particles actually are highly energy positively charged helium ions emitted from naturally occurring radioactive elements such as radium. Actually, these are this is the picture. If you observe in this one, in this picture, lead block containing source of radioactive alpha particles given in one end, and these alpha particles falling on a thin gold foil, and a beam of alpha particles is coming onto that foil, and there are some deflections, and a circular zinc sulfide fluorescent screen is also kept around it, around the foil. And finally, they notice that some of the alpha particles are deflected, means scattered at large angles, and most of the alpha particles are said to be undeflected in that case. So in this figure, the zinc sulfide fluorescent screen was used to detect the alpha particles that had passed through or been deflected by gold foil. So this picture is very clear for this Rutherford scattering experiment. So that means what are the conclusions in this one is most of the alpha particles went through the gold foil and some were deflected slightly as expected, but some particles were deflected by very large angles and some even bounced straight back towards the source. So that's what from the picture we are telling. That means these particles have collided head on with what we know to be nucleus and the gold atom. That means how these particles collided, the head of the nucleus, that means head of the gold foil means that is nucleus. Okay, as a result, Rutherford described the results of that theory as it was an incredible, as if you had fired a 15-inch artillery shell at a piece of paper and it came straight back and hit you. So this is like that example. Now, based on that Rutherford explanations on the fact that gold foil consists of thousands of gold atoms, when a beam of positively charged alpha particles bombarded the foil, the majority of the particles passed through the undeflected, and since the atom consists of mainly of empty space. However, at the core of the atom lies a dense region of positive charge called nucleus. When the alpha particles came close to the nucleus of the gold atom, it deflected through a large angle, and when it hit the nucleus, deflected back along its initial path. So, in these conclusions, he noticed that alpha particle, when they bounce back at a particular point in the atom, that is nothing but a nucleus. So in this picture, if you observe, particle deflected through a large angle is shown here, and beam of alpha particle is moving with this red line here showing and deflected particles are shown here, and reflected particle with the back arrow mark here. shown. That means Rutherford's model explains his findings in gold foil experiments in this picture. Moving on to the scale of the atom. Rutherford work has formed the basis of much of our thinking on the structure of atom, and Rutherford removed to have said to his students that all science is either physics, or stamp collecting only. That means the vast space in the atom compared to the tiny size of the nucleus is hard to fully appreciate. That means Rutherford native New Zealand is a great rugby playing nation, and imagine being at Eden Park Stadium that you can see here, figure number 6 here. This is the Eden Park Stadium, Auckland. This is Rutherford native. Looking down the center of the pitch from the top row of the seats on the upper tier of the stand, you can see that a very small grape was placed at the center of the field. The distance between the grape and U would represent the distance between the electron and nucleus. That means lot of space is there, empty space is there in the ground. Like that only this atom and its structure as assumed. So here he told that relative volume of open space in the atom is vast, and our simple representation of Rutherford's atomic model in this figure we have observed this figure 4. So figure 4 I will show you once again. This is the deflection figure. Okay, figure 4, obviously unrealistic, that is right. So this is very clear to understand from Rutherford's theory, this cricket stadium. The nucleus occupies a tiny volume of atom, and the diameter of the atom is approximately 1 lakh times the diameter of the nucleus. And we shall return to the idea of the scale of the atom in the next topics we'll see in the next lectures. Now let us see. Atoms themselves are extremely very small according to Rutherford, and also the diameter of most of the atoms is in range 10 power 10 to 5 in 10 power 10 meters. Unit used to describe this one is picometer, PM, 10 power minus 12 meters, that is. And in X-ray crystallography, commonly used unit of atomic dimensions is angstrom units. So 1 angstrom is 10 to the power of minus 10 meters. For example, the atomic radius of fluorine atom is quoted in the data booklet is 60 into 10 to the power of minus 12 meters, means 60 picometers. To convert this into atomic angstrom units, we'll use dimensional analysis. That is nothing but converting 60 picometers into angstrom units. That is 6 in 10 to the power of minus 1 angstrom unit in this conversion. And another one, subatomic particles and descriptions of atoms. After Rutherford experiment 1909, the number of experiments of Rutherford's experiment, number of experiments followed a period of approximately about up to 1935, culminating in scientists having a much more detailed picture of structure of atom. Atom consists of 3 types of atomic particles: proton, neutron, electron. According to this data from that collection, the atomic mass unit is 1.66 in 10 to the power of minus 24 grams. Proton, neutron, electron. Charges with the masses and their locations given: proton located in nucleus, neutron located in nucleus, electron located outside the nucleus in the electron cloud. And mass of the electron is 1 by 1836 compared to proton. And the neutron was discovered by British physicist James Chadwick in 1932. Is Chadwick here, picture diagram we are observing. Using Chadwick's discovery of neutron was based on the experiment with beryllium placed in a vacuum chamber was bombarded with alpha particles emitted from polonium, and the beryllium was found to emit neutrons based on Chadwick's mass calculations. Was able to prove categorically the particles were in fact neutrons and not gamma rays had been previously thought, that is gamma rays, that is 2 alpha, that means 2He4 beryllium gives carbon 12 and neutron. So neutron 0N1 is a symbol. This is a nuclear chemical equation, and the discovery of neutron was at the time the last piece of the jigsaw puzzle of atomic structure. That is, of that Rutherford always postulated existence of the neutron but no conclusive evidence until Chadwick's discovery. So he is telling about neutron, but you don't have any kind of evidence of existence of neutron, Rutherford. So finally Chadwick succeeded in that manner of discovering it via this nuclear bombardment of helium nucleus with beryllium. Of that atomic number symbol is given Z, that atoms of each element have individual atomic number Z. So atomic number is nothing but protons in the nucleus. The different elements have different atomic numbers given. Z of oxygen is 8, Z of copper is 29. That means oxygen has 8 protons and 8 electrons. Copper is having 29 protons and 29 electrons. What is the mass number symbol? A. Mass number symbol is A, and the mass number is nothing but number of protons plus number of neutrons. Z for fluorine is 9. Therefore, fluorine has 9 protons and 9 electrons. And fluorine 19 is nothing but 19 minus 9, 10 neutrons are there. So to find the number of neutrons, we have to subtract the number of protons from the Z value, from the mass number value, right? So 19 minus 9 is 10 neutrons came in the fluorine 19. Neutron number is 10. So nuclear symbol here very clearly given. Nuclear symbol includes A and Z. Particular element X represented like this ZXA. And in this one we have different forms. The same element have same atomic number is there. That's what we called as isotopes. Here hydrogen is having proton, 1 proton, 1 electron, 2 neutrons. That is tritium. Hydrogen 3 isotopes in that. Tritium is given like this. That is 1H3. 1H2 deuterium, 1 proton, 1 electron, 1 neutron is there. And hydrogen 1H1, that is called as protium. 1 proton, 1 electron, 0 neutrons. So one of the isotopes of hydrogen which is not having neutrons is protium. In nature, most elements exist in a mixture of isotopes. For example, boron contains 2 natural occurring isotopes, boron 10. Natural abundance is 19.9, boron 11. Natural abundance is 80.1 is there. This is one example of naturally existing boron percentages. Likewise, we have uranium 35. Uranium 230 is 5, 234, 238, and their relative abundance is also in this chart. They have provided us to understand the things here. They have calculated the number of neutrons. Uranium 234, we have 142 neutrons. Uranium 235, 143 neutrons. Uranium 238, 146 neutrons are there. Number of protons is 92. Why? Because Z value for uranium is 92. And while that of number of electrons is also the same. Coming to the radioisotopes, we have radioisotopes are there as well. Boron 10 and boron 11 as the number of radioisotopes are there. Example, boron 8 and boron 9, boron 12, 13. These are all radioisotopes used in nuclear medicine diagnostics, treatment and research, as traces in biochemical and pharmaceutical research, as chemical clocks in zoological and archaeological dating. Iodine radioisotopes, medical traces are there. We have the thyroid gland in the neck releases thyroxine and triiodothyronin into bloodstream. So how this thyroid gland in the neck releases thyroxine and triiodothyronin into bloodstream is nothing but this because of the hormones and the chemical messages control the body growth and metabolism. So an overactive thyroid gland produces excess of these two hormones in this accelerates the metabolism of a body, leading symptoms such as high levels of anxiety, goiter, another disease, that is swelling of thyroid gland, and weight loss. So two things are there, thyroid, two problems are there to this one. Okay, iodine is concentrated in the thyroid gland, where it is there in the thyroid gland it is there. And radioactive isotope iodine 131 emits gamma rays and a high energy short wavelength photons. Iodine 131 is said to be used in treatment of thyroid cancer and also in the diagnostics to determine whether the thyroid gland is functioning normally and all. We will check, we'll use this iodine 135. This is the real picture that was taken. So a single photon emission computed tomography scanner, this is called tomography scanner, used to detect the gamma rays from iodine 135. In hospital, a patient is given radioactive iodine 135, then the image of the thyroid gland can be obtained, and for example using gamma camera. In contrast, iodine 125 is used to treat prostate cancer and brain tumors also. So many uses are there. Iodine 135 for prostate cancer and this brain tumors. Iodine 131 is for thyroid related problems. And positron emission tomography is there. This is the scanners here we are showing in the diagram. Scanners give three-dimensional images of tracer concentration in the body. Can be used to detect the cancers. Single photon emission computed tomography, that is SPECT imaging, can be used to detect the gamma rays emitted from iodine 131. So many different kinds of technologies are used at that time. That is iodine 135 is used. From that, how gamma rays, how many gamma rays can be detected or not. So that is one most important application of radioisotopes. Coming to the cobalt 60 is used, emits also emits gamma rays and used in the treatment of cancer. So it is also used, most important application of cobalt 60. And carbon 14, cosmic, geological and archaeological dating. These are the most important one. The radioisotopes are often used in radioactive clocks for the dating of cosmic, geological and archaeological matter. American scientist Professor Willard Libby won the Nobel Prize in Chemistry in 1960 for his method that uses carbon 14 of age determination of archaeology, geology, geophysics and other branches of science. So carbon 14 is most important one. And coming to the nitrogen is present in the Earth atmosphere. As you know, isotope nitrogen 14 is atmosphere constantly bombarded by highly penetrating cosmic rays from the outer space, and this neutron bombardment causes radioactive carbon 14 to form along with hydrogen. According to the reaction here, 7 and 14 is there. When nitrogen 14 is isotope is bombarded with neutron, then only this carbon 14 will be developed in this nucleochemical reaction. This neutron bombardment results constant supply of carbon 14 in the atmosphere, and it's continuously formed from nitrogen 14. So nitrogen gas consists of 78% in the earth air by volume. Because of this only, so many this carbon 14 isotopes are possible in this neutron bombardments. And they studied the half-life of that at the time that takes for an amount of radioactive isotope decrease to 1/2 of its initial volume. So half-life definition also here given. Half-life of carbon 14 decay process is noticed as 5730 years. So it is a big value to understand why this is used. Carbon 14 can be oxidized to form carbon dioxide. Living plants absorb carbon dioxide for photosynthesis, assimilate the carbon into other compounds in other bodies. Animals consume plants and taking the carbon compounds and then exhale carbon dioxide. In all living organisms, the ratio between carbon 12 and 14 found in the atmosphere is essentially constant at any given time. Since carbon is continually exchanged with the atmosphere in the process of life, so when a living organism dies, however, carbon is no longer exchanged with the atmosphere or with other organisms. So we can understand when the living organism is there, okay, the exchange of carbon takes place from the atmosphere into the body. Once the body died, so then there is no kind of exchange. In that way, we can understand that there's so many kinds of applications are there in this science, and that carbon-14 isotope may then undergo decay to form nitrogen-emitting beta particles in the process. Here, carbon-14 giving nitrogen-14 and one beta particle. So the net result in this is nothing but a gradual decrease in the ratio of carbon-14 and carbon-12 in the organism's body. An amount of carbon-14 in the body of the plant and animal was once living can be measured. Scientists can use this method to determine the age of artifacts such as wood, paintings, papyrus, ancient manuscripts and scrolls. This is the shroud of Turin. Shroud of Turin is nothing but a linen cloth believed by many people to be used wrap in the body of Jesus Christ after his death. The cloth shows that image of person who appears physically traumatized, and many believe that it represents the crucifixion of Jesus. 1988, the Vatican in Rome commissioned 3 independent analytical laboratories based in the University of Oxford and Swiss Federal Institute of Technology, University of Arizona, USA, carry out carbon-14 dating in the shroud. Tell me, what is shroud? The shroud of Turin. It's a linen cloth, nothing but is believed to many people to be one used in the ramp. And all the 3 results confirm that the samples taken from the cloth originated between 1260 and 1390 AD, suggesting that shroud was not the burial cloth of Jesus. Nevertheless, the controversy, the debate about the shroud continues among scientists, theologians, and historians to this day. So, up to today, there is a full controversy is there on this one. In July 2013, Galileo Fanti and co-workers from the University of Padua, Italy, published research journal Vibrational Spectroscopy, which shows the two-way relationship between the age and spectral property of ancient flax textiles. And media reported that finding worldwide claiming that results dated showed thorium between 300 BC and 400 AD, which could date from the time of Christ. So that is what about this one. After that, there is relative atomic mass discussion which was taken. So relative atomic mass. We will see relative atomic mass. This relative atomic mass of electron is negligible, 1 by 1836, mass of atom is concentrated in the nucleus and the protons and neutrons are there in that. However, the mass of single atom is tiny and subatomic particles stable we observed. Atomic mass unit also we have given, the more correctly termed as unified atomic mass unit according to UPTO, and relative atomic mass is defined as that atomic mass is nothing but unified atomic mass unit is the non-SI unit of mass, and it defined 1/12 of the mass of carbon 12 atom in its ground state. What is unified atomic mass unit is this one, 1/12 of carbon 12 atomic mass, and this unit is used to express the mass of atomic particles such as 1 AMU, or 1 unit is 1.66 in 10 to the power of minus 27 kilograms. Of that, the relative atomic masses, AR, we'll see symbol AR, is the ratio of average mass of atom to the unified atomic mass unit. That means, as mentioned, we have subatomic particles are there. The average mass of the atom is weighed, average atomic mass of isotopes and their relative abundances. Now, how this relative atomic mass discovered, you see? mass spectrometer used here. This is the device instrument used to determine the relative atomic mass. This is isotopic composition here taken, and this heating filament of vaporized sample stage 1. Inlet here is provided. Inject the sample and electron beam to ionized sample here. This is after that electron beam will come like this. The positive ions are accelerated in the electric field, and magnetic field which is perpendicular to that one here, magnet is kept here. After that, once the beam is moving, detector towards detector, and heaviest particles deflected least and lightest particle deflected most here, shown in this picture. That means in stage 1 what happened? The sample is injected into the instrument which is heated and vaporized, producing the gases, atoms or molecules. And stage 2 ionization taken place. In stage 3 acceleration of these ions is taken place. In stage 4 deflection. Stage 5 detection. Here the mass spectrum of boron here studied. The 2 peaks corresponds to 2 isotopes boron percentages composition here notice. That means boron 10 19.9 percentage area under peak here, this is, and this one other peak is 80.1 is there, another one boron 11. That is the percentage of abundance is here noticed from this experimental results. After that only this example problem here given, and relative mass is nothing but we have to just multiply the atomic mass number with the percentage of abundance to get the relative mass. 10.8 is the answer for this problem. Likewise, we have rubidium is there. Rubidium 85 and rubidium 87 with the percentages are there. And their atomic mass units 84.91 exactly. And percentage here they asked what is the composition of units. We don't know the compositions, then what we'll do is composition percentage is assumed as X for rubidium 185, and 100 minus X will be the another second isotope. After finding the X, we got the 72 value is the percentage of 85 rubidium, and remaining is 28% is rubidium 87. Likewise, we have so many other kinds of examples are there. Deduce the relative atomic mass of element X from its mass spectrum. Identify in the figure, identify the X in the periodic table. Here, this is the mass spectrum picture here given. That means, and this is how they have calculated the mass spectrum shown two isotopes is X69, X71. Here one is 69, another one is 79. Theory of area under covered peak here percentages, if you check it in that, X69 is 27, peak came up, exactly this is 27. Another one came that is exactly at 41 units here, that is noticed. Natural occurring isotopes must have total value is 100%. So here the 41 plus 27 is not that much. So total weight of both peaks is 68 units is there. Total weight, and the relative atomic mass of X is need to be determined. Relative atomic mass how determined here is 27 by this 68 into 100 got 40%. So that means the other one is 60. So relative atomic mass of X can be determined here using percentage of this X60. 9 is nothing but 40%. So multiplied the mass number with percentages and they got 70.2. Approximately 70 is the correct one here for this answer. So once we got 70 as the mass number, the 70 is the relative atomic mass, that is for gallium, Z value 31 in the periodic table, and the data of the value of 70.2 from the calculations closest to this one. That's why we went for this gallium the calculation, and the precision of the calculations will be 2. So that the reason why the figures are expressed in the 2 SF is nothing but this is went for the precision category, and 2 digits we have taken, that is a specific figure, significant figure we can say, that is 69.74. Figures were expressed in two significant figures here, 69.74. Here, this picture given in the problem, otherwise we can't do this calculation. This is another one. This is the model only example I have shown. Okay. So these are the problems we have discussed in this concept. Next, we have the concept of electromagnetic radiation. We'll see what is electromagnetic radiation. That means so Samuel Beckett, Irish novelist, poet, and playwright who won the Nobel Prize in Literature in 1969, he developed this electromagnetic radiation. That means developments led to the much of our understanding of the electromagnetic structure. Atoms come from experiments involving light, visible light we see, and full of scientific intrigue. Visible light is one type of electromagnetic radiation. Other examples we have included radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, gamma rays, and all. Electromagnetic spectrum, EMF, is a spectrum of wavelength that comprise of various types of electromagnetic radiation, and that the energy E is inversely proportional to the wavelength. The high energy radiation such as gamma rays and X-rays have small wavelengths. Low energy radiation such as radio waves have long wavelengths. So wavelength is related with C is equals to nu lambda as per the electromagnetic theory, and where C is called speed of light given taken as 3 × 10⁸ meter per second. SI unit of this energy is joule, and wavelength is meter, and the frequency is hertz. Hz will use. After they studied about the absorption emission continuous spectrum, the white hot metal object such as incandescent light bulb filament emits full range of wavelengths producing continuous spectrum, including all colors of rainbow from the red to violet. If a pure gaseous element such as hydrogen is subjected to an electrical discharge, gas will glow. It emits radiation. The resultant emission spectrum consists of series of lines against dark background. Here you will observe if a cloud of cold gas is placed between the hot metal and the detector, absorption spectrum is observed, and this consists of a pattern of dark lines against a colored background. The gaseous atoms absorb certain wavelengths of light from the continuous spectrum. Our absorption spectrum and emission spectrum are widely used in astronomy to analyze light from stars. So this picture, if you observe the side picture given, aurora borealis in Lapland, Sweden. This is in Sweden. They have observed this is the northern lights is a display of colored light visible in the night sky at high latitudes. It occurs when charged and energetic particles from the sun are drawn by the Earth's magnetic field to the polar regions. Hundreds of kilometers of they collide with the gaseous molecules and atoms, causing them to emit light like this. It's night time. This is. It's an example, an interesting example. Next one, emission spectra. Emission spectra we'll see. Both three we'll see next lesson. Okay. In 1600s, Sir Isaac Newton showed that if sunlight is passed through a glass prism, the visible light is separated into different colors, generating continuous spectrum. This spectrum contains light of wavelengths, so appears as continuous series of colors, each color merging into next with no gaps. That's why it's called as continuous spectrum. A familiar example, you know, that is continuous spectrum is rainbow. We are observing in this picture. White light is perceived by the human eye, consists of many colors or wavelengths of light shown here. Continuous spectrum of white light emitted in incandescent light bulb filament. Many sources of radiation produces line spectrum rather than a continuous spectrum. If a pure gaseous element is subjected to high voltage under the reduced pressure, then gas will emit certain characteristic color of light. And for example, you have taken sodium emits yellow light, and thus light is passed through a prism. This is yellow light sodium shown in the picture. And resulting spectrum is not continuous, but consists of black background with a small number of colored lines, each corresponding to characteristic wavelengths. That's what we have studied in the previous observation of electromagnetic radiation, and line spectrum. And each element has its own characteristic line spectrum, which can be used to identify the element. So every element has a characteristic line spectrum is there, because this is a discontinuous spectrum. For example, the visible region of line is there, emission spectrum sodium, two distinct yellow lines are corresponding, wavelength 589 and 589.6 nanometers. You can see this background. After that, they identified flame test also in our chemistry. In this picture, we observe line emission spectrum of sodium. You see the lines is 589 and 589.6 nanometers shown in this picture. So although this picture is showing in one line, but that line corresponds to two frequencies, two wavelengths. There are two lines separated by a dark background. And coming to the application of this one is flame test is often used in laboratory to identify certain metals. The color of the flame varies for different elements, can be used to identify unknown substances. The color due to the excitation of electrons in the metals by heat of the flame. As electrons lost energy they have just gained, then they emit photons of light. That's what they discussed about quantization energy. Max Planck given E is equal to h nu expressions and h value for the quantum theory and all that. That's what we have discussed in the sessions also. Okay, it's fine. We'll go back to the beginning. That means what we have discussed in this topic is atomic structure introduction and some theories and relative atomic masses and their discovery by this mass spectroscopy, spectrometer, and radioisotopes and their applications, and symbol of the atoms, isotopes, isobars. There is some data information related to the subatomic particles, charge, mass, and their location, as well as the fundamental theories of atom. That's what we have studied in this lecture. Hope you have understand this lecture. This is actually the entire IB board textbook related information in the atomic structure, continuation of the lecture, whatever I have discussed in the previous one. So this lecture also we have discussed about atoms and their basic theories. Okay, hope you understand, and watch for the next lecture. It will be released in the next day, tomorrow, for atomic structure continuation, and we will take one concept and we'll see the different books to understand how the concept is given. Okay, that way we can understand the entire information on one topic in our classes. Okay, thank you very much. Have a nice day, and please ask your friends and students to subscribe my channel to see my regular classes. Thank you very much.